All right, we were on black holes. I just want to start here once again. So with neutron stars, right? Remember, we're talking about very massive stars. They started out more than 8 times the mass of the sun, and they've undergone the supernova explosion, and then there is material remaining. And if we have between 1.4 and 3 about 3 solar masses, the star can hold itself up against completely collapsing, and that's of course using what would be called neutron degeneracy pressure. We talked a lot about that already. All right, so now comes the question: what happens beyond three times the mass of the sun? So if the core that remains, so this is again after the supernova explosion, if the core that remains is around three times the mass of the sun, then it turns out that there's nothing that can prevent, even neutron degeneracy pressure cannot hold up against gravitation of that magnitude, and the star will completely collapse. Now let me put a couple of little question marks. We think that it's about 3 times the mass of the sun. We think that the effects of rotation and also of the strength of the magnetic field will also contribute, and so it's around. We usually say it's around 3 times the mass of the sun. It's not some exact number that we have, but right around that mass. We don't think anything. It doesn't matter how fast these things are spinning or what the strength of their magnetic field is. They will collapse. It might be slightly more than this. Again, with the considerations of magnetic fields, the strength of the magnetic field, and the rotation rate. The millisecond pulsars, right? The ones that are rotating around, rotating around once every 1,000th of a second, or shorter than that, slightly shorter than that. Those might take a little bit more than 3 solar masses, but not much. I mean, so not, we're not talking about like 4 times the mass of the sun or anything like that. All right, so it's around 3 times the mass of the sun. Nothing holds it up. It'll completely collapse, and we call that a black hole. And the reason it's called a black hole is because it turns out that light itself, right, the fastest thing there is in the universe, will not escape the black hole. All right, so let's dive into this. People have been studying this certainly in great detail since the 1960s, when these things were first. They were somewhat proposed before that. There's some publications where some people just mention the possibility of these things, but they really started to be taken seriously in the 1960s. All right, so there is this distance from the center of the black hole. The distance from the center of the black hole is called the Schwarzschild radius, and actually Schwarzschild was a guy who lived during the time of World War I. So this was a very, very long time ago, and he worked out a very simple. If you look, there's the equation for what's called the escape velocity, right? It's a very simple equation. The escape velocity that Isaac Newton actually was the one that came up with this over 350 years ago. The escape velocity for an object is equal to the square root of 2 times this constant big G times the mass of the object divided by the radius. And so what Schwarzschild did, this is again a little more than 100 years ago, is he said, all right, well, what if the escape velocity was the speed of light? Now he didn't know anything about black holes or anything like that, but he said, what if What if the escape velocity was the speed of light? And so he took the r in that equation for the escape velocity and solved for r, for something that, that had an escape velocity of the speed of light. And so that's been called the Schwarzschild radius. All right, and so it turns out that that is actually the radius of the of a black hole. All right, so and you can now here's the thing. So the Schwarzschild radius, you can actually calculate it for any object that has mass in the universe. You could calculate the Schwarzschild radius of the Earth, for example. It turns out, the Schwarzschild radius of the Earth is really, really tiny. It's around a centimeter or so. I forget exactly what the number is, but you just put in the mass of the Earth and the speed. You use the speed of light as your escape speed, and so the Earth would have to shrink down to about a radius of about 1 centimeter. In other words, its diameter would be roughly 2 centimeters. The Sun would have to shrink down to about 3 kilometers, which is still pretty tiny for the Sun, but so a diameter of about 6 kilometers. Now here's the thing: the Schwarzschild radius, it's wonderful. You can do these calculations on any object. I mean, you could talk about the Schwarzschild radius of a building or whatever, but there's no mechanism for an object like the Earth or the Sun, the Sun is a pretty massive object, but there's no mechanism to cause the Sun to shrink down to a radius of 3 kilometers or a diameter of 6, right? There's no way for that to happen. So the only way that these things happen is with a collapsing, massive dead star. And when you have 3 times the mass of the Sun or more remaining after the supernova explosion, then these things will collapse. All right. So now we're going to consider the black hole itself. So within the black hole, okay. So the distance from the center of the black hole to the outer edge, which we now know is called the Schwarzschild radius, that area is also known as the event horizon. And the reason for that has to do with light, right? So remember, you're talking about a region where anything within that region, between the center of the black hole to the edge of the Schwarzschild radius, would have to achieve a speed greater than the speed of light to leave, to reach escape velocity. When, of course, you can't reach escape velocity because nothing in the universe travels faster than light. So that's why these things are called the event horizon. If there was some object and you could observe it going into the black hole, it would literally, all events that happened on that object, let's say it's a spaceship or something like that, would cease to be observable. We would not be able to see them. They would be beyond what's called the event horizon. Just like the horizon on the Earth, right? There's stuff because the Earth curves away from us, right? Wherever you're standing, there is a horizon, right? So, the Sun dips down below the horizon, and of course it's nighttime, but the Sun's still there, right? It's just not within our view. And so this is the way that we approach this with black holes. There's the stuff that's going on inside of a black hole is certainly going on, but we cannot observe that. All right. Let me talk a little bit about, because we'll talk about the speed of light and Einstein's theory of relativity. So there's actually 2 parts to Einstein's theory of relativity, right? The thing that he invented in the idea of special relativity, which he came up with in the year 1905, that's really what gave us the famous equation E equals mc squared, right? Energy is equal to mass times the speed of light squared. So that actually comes out of Einstein's ideas on special relativity. And so what Einstein was doing, and how he came up with this thing called special relativity. But by the way, that's not what he wins his Nobel Prize for. It was something much more mundane. Well, not really mundane, but the special relativity was too radical of an idea. And in science you can come up with some radical ideas, but they have to be there has to be an experiment that you can perform. And during most of Einstein's life, really only towards the end of his life, in the 1950s, were actual experiments that were performed that were able to measure some of these effects. Okay, Einstein won the Nobel Prize on what is it called? What's called the photoelectric effect. It's a quantum mechanical property. But anyhow, that's actually what he wins the Nobel Prize for. Again, this was too radical for people back then. Well, really, because you just didn't have experimentation. We didn't have the technology to experiment on this. All right, so this is the basic idea. Einstein realized that the speed of light was a constant throughout the universe. That's really what the special theory of relativity is all about. And so there are consequences for the speed of light to be the same. All right. So, for example, if you think about like a car or something like that, like this picture right here. So this is what we would call Galilean relativity. So Galileo actually came up with the mathematics for this. It's very simple. If the car is traveling at 100 kilometers per second, or I guess per hour here, 100 kilometers per hour, and then somebody fires a gun, that's riding in the car at 1,000 kilometers per hour, then the speed of the bullet is, to some observer on the ground, is moving at the speed of the bullet plus the speed of the car, right? You just simply add the velocities. So that's a pretty simple idea. I mean, there's nothing amazing about that. But what is amazing is during Einstein's time, where, people weren't even thinking about spacecraft or anything like that, he realized that, well, it doesn't matter. This is true for bullets, and you throw a ball or something like that. You can add the velocity of the vehicle to the velocity of the ball, or the velocity of the bullet to the velocity of the vehicle. But when it comes to light, like if this car were to turn on its headlights, this observer here it doesn't matter how fast this car was going, the observer would always see the light coming from the headlights at the speed of light. That's pretty amazing. Okay, so that's what Einstein reasoned. And now if you think of it in terms of a spacecraft, right? A spacecraft traveling very, very fast. So this is traveling at 10% the speed of light. That's what that means, 0.1 c. So something traveling at 10% the speed of light. The beam of light that leaves the spacecraft, some observer would always measure the speed of light to be exactly the same. Right? And so that's what leads to this idea of special relativity. Okay, so there's certain things that happen. It's like the universe makes sure that the speed of light is always the same for all observers. All right, so what are those things that happen? Basically, two major things that happen. Well, one of the things that Einstein realized is that there's no absolute frame of reference. So it doesn't matter, the person standing on the ground, or, it's often easy to think of the Earth as being the absolute frame of reference. But of course, the Earth is spinning about its axis. We're moving around the sun. The sun's moving around the galaxy. The galaxy's moving, with respect to other galaxies. So there's no absolute frame of reference. And it turns out that time and space are not independent of each other. Einstein even came up with the term space-time. So that for the speed of light to stay the same for all observers, space itself and time itself